Hello everybody, it's Amrit. Today we'll be trying to solve the definite integrals from infinite to 0 of e to the negative x squared cos of 5x dx. So this can be done using an integral technique called the Feynman technique created by Richard Feynman. So basically, what's involved in this integral is we're going to set this whole function, we're going to take this whole function to f of something. So we're going to we can make any variable. Let's call it k for this one. We're going to say that f of k is equal to the integral of definite integral from infinite to 0 of e to the negative x squared cos of, we're going to, instead of 5x this time, we're going to say kx. So basically, we're saying that this integral top here is equal to f of 5. So this one is f of kx dx. So now, what we can do with this is we can differentiate both sides. And if you didn't know, a differentiate of this integral can go inside there. So this basically comes the f prime of k is equal to the integral of from infinite to 0 of d of dx of e to the negative x squared cos of kx dx. So now, what can we do with this? Well, we can use partial derivatives to solve this one. So, we can actually, in this, we have to pretend now that k is the actual variable and x is just a constant. So, what we're going to do is we're going to find what's the derivative of e to the negative x squared is e to the negative x squared, because remember x is just a constant this time, and the derivative of this will be negative sine of kx. And remember, because x is our constant, we're going to put the x right here. So that occurs, and we're going to say that's the integral from infinite to 0 of d of x. So this is a good start. Now, we can use integration of parts now, like we couldn't do in this original, but now we can do it to solve this. So we're going to set u equal to sine of ax, sine of kx, and v is going to equal to negative x e to the to the negative x squared. So we can differentiate this first one, and this will get us. We're coming back to our original where we said that it was we said originally that this was sine of kx, and k was the variable. Now x is back to our variable, so this becomes the du is k sine kx, and this is dv, by the way, sorry. And if we say we're gonna integrate that, so v is gonna equal to, you can do this in your mind, half times e to the negative x squared. And actually, this can be said as 1 over half of e to the negative x squared could be said e to the x squared 2 over 1. So we're going to rearrange it to that. So now we can use integration of parts to solve this. So using our known integration of parts, we're going to say that the sine of kx over, we said here, 2ex squared, and this is in the bounds of infinite and 0, minus so you're going to have a constant there that is k over 2. So we're going to take the k over 2 out. So I'm the integral from infinite to 0 of e to the negative x squared, e to the negative x squared cos of kx. So this is what we're going to look at. So using this, we can actually find this because we have a definite integral over here. So this is just equal to, we're going to see that if we put infinite into this as x, you're going to see that that just comes to 0 because you're going to have a large denominator, very large, and it's going to be 1 as the numerator, and you're going to have, so that's going to be equal to 0, and you're going to minus that by the definite integral of this, which is actually also, I mean, when you plug in 0, that's also 0, so that's equal to 0. So this can be just rewritten as 0, and remember, this 0 doesn't matter, so basically this is the rest of our integral. So, and if you may have not noticed, sorry, this is supposed to be a dx here, this integral from infinite to 0 of e to the negative x cos of kx dx, if we go on to our second step, we see that that was basically our second, what we said, and we set this as f of k. So basically, f prime of k is equal to negative k over 2 f of k. So now, this is an important fact we can use. Now, this is just separable because we have the derivative and the regular function in the same thing. So, this is just going to be equal to df over dk is equal to negative k over 2 f. This can be rearranged again to df over f is equal to negative k over 2 dA. Now, you can differentiate both of these. So because this df is basically acting as the dx, the rest is 1 over f. So this is just ln of f is the integral, absolute value of f. And the integral of this, well, it's basically just the regular x to the n rule, how you integrate that. And that's going to, you're going to get k, negative k squared over 4 plus c. Now, I think a good way, because especially a long integral like this, you're probably going to see, sorry I took this away, you're probably going to find some other constants, so we're going to call this C1. So now, based on this, we can basically say, we can set E, we can do E to both of these, so that's going to be equal, so you're going to get, based on that, F of A, so sorry, f of k, I keep thinking a is k. Yeah, by the way, this is actually, when I said f here, it's basically just f of k, basically. So f of k is equal to, well, you can use our rule, the constant will be multiplied by, and this is a new constant, by the way, times e to the negative k squared over 4. So basically, this is what we're saying. We're saying basically that our integral, because we can plug in back in our original one that we said was e to the negative x squared cos of kx dx is equal to c2 times e to the negative k squared over 4. So when we do something like this, if we want to find a constant, we can plug in any value. So let's see what we can plug in. Well, if you want to plug in, we have two variables, but you want to get rid of both of them. And the only way we can probably do that is call it 0, because 0 times x is equal to 0. So that eliminates it and makes a constant. So we set k equal to 0. What does that do? Well, cos of 0, of course, is going to be 1. So basically, if we, and we also have a 0 here. So basically, we're going to get and remember, this is going to be equal to e to the 0, which is equal to 1. So basically, we're getting that the integral from infinite to 0 of e to the negative x squared dx is equal to c2. Remember, this is our integral now. Now we just need to solve this integral. Now, you may remember there's this integral that's very similar to this. And it actually is exactly it, basically, except the bounds are different. And that is the Gaussian integral. And it's basically saying that the integral from infinite to negative infinite of e to the negative x squared dx is equal to square root of pi. Now we can't have that. We have from integral to infinite to 0. But if you should remember that this is basically just 2 times the integral of infinite of 0. This here is that. So basically this is just 2 times what we want. So we can divide this thing by 2, divide this by 2. So then that's why when we get the integral of from infinite to 0 of e to the negative x squared dx is equal to square root pi over 2. So we figured that square root of pi over 2 is equal to our c2 in this case. Now basically we can use our original function. So let me go here and this will complete it. So we have f prime of k is equal to the integral from 0 of e to the negative x squared cos of kx dx. But remember, we also stated that f of k is equal to c2 e to the negative k squared over 4. So let me erase some of this stuff that we already know. So that is also equal to square root pi over 2, which was our given constant, times e to the negative k squared over 4. And based on this, we can state that we can use the fact that so we now know that oh yeah, sorry, this was equal to, sorry, I put f derivative here, but this is just equal to f of k. This is also equal to f of k. So this is basically what we got. Now remember in the original one we had cos of 5x, and it had blah 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 equal to f of 5, and we did f of k to get its blah 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 cos of kx. So we can just sub 5 into that. Sorry, we can just put 5 into that. So our final integral f of k is equal to square root pi over 2 e to the negative 25 over 4. And that is our integral. Thank you for watching.